So, hello everyone on YouTube as well. So, today we are meeting for week 11 discussion. And what are the things we have done in week 11 contents is the Fubini theorem. So, let me just write the Fubini theorem first, then I'll give some time to uh, ask questions. Fubini theorem. It says that if of course, we need to start with some measured spaces. Xa mu and yb mu, they are measured spaces, and mu and nu are sigma finite, and suppose f from x cross y to r, this is a times b measurable that satisfies one of the following. So what are all the conditions? One is f is non-negative, or f is in L1 x cross y, or the equivalent condition that integral x integral y mod fxy d nu y d mu x, this is finite, or the fourth one is integral y integral x mod fxy d mu x d nu y, this is finite. Then if f satisfies any of these conditions, then we conclude that the integral of f in the product measure mu cross nu over x cross y, this can be evaluated by using either you integrate with respect to y first and then integrate with respect to x, or first integrate with respect to x, then with respect to y, and then we'll get the same answer, mu x d nu y. So this was the Fubini theorem. Today we'll see some applications of this indeed. But yeah, so if anyone has any questions, they can ask.
Sir, regarding previous assignment, there
Uh-huh.
is some question that I need to talk to you.
Yes, yes.
So it says that if x a is a measurable space
Mm-hmm.
and E belongs to the product measure A cross Borel sigma algebra
Right.
and alpha beta belongs to real number,
Uh-huh.
then the set x comma t is such that x comma alpha t plus beta belongs to product measure A cross Borel sigma algebra belong to the product measure, sorry, x comma alpha t plus
Yeah,
beta
I have the
belongs to E.
question.
That set belongs to the product measure A cross Borel sigma algebra.
Right, right.
I have seen this in the book also. That it is given that you should try with the sigma algebra technique.
Correct.
So I don't get it how rectangles should belongs to the set. First, if you want to show that by the sigma algebra technique, then first the
Mm-hmm.
rectangle should belong to that set, and we have to show that that set is sigma algebra.
Correct.
Yes, sir.
Yeah. Okay, okay. I think Robin also had the same question, right?
It is the first question of assignment first. Assignment number 10.
Aniruddha, if you can just show what the sigma algebra, how we can apply the sigma algebra technique.
Right, right. So I am planning to do that. Have you tried it though?
No, I haven't.
Okay, okay, no problem. Actually, I mailed you a bit late. I was intending to mail you last night, but I forgot. So anyway,
Exactly.
Okay, let us try to do that. See, what is given to us? XA is a measure space, and we are saying that let us take a set in A product BR, where BR is the Borel sigma algebra, and let us construct another set SE alpha beta. What is this set? This set is a collection of all x comma t in x cross R, such that x comma alpha t plus beta, this is inside E, right? And the claim is for every such E in A cross B, and of course for every alpha beta, just a minute, yeah. And for every alpha beta in real numbers, this SE alpha beta, this is inside A cross BR, right? So does everyone agree with this? This is our claim.
Yes, sir. The E should be the fixed one.
Yeah, but that should be for every such E, right?
Yes, sir. Yes, sir.
Okay. So what we'll do is let us start with the collection C. Let us define this C as collect all those E inside A cross BR such that SE alpha beta, this is inside A cross BR for every alpha beta. So given this collection, what should be the first question that comes to mind? Yes. Yeah, Prasandeep, can you tell me? See, what should we check first here in this collection?
You are using the sigma algebra technique.
Right, right. I'm going to prove that C. See, one thing is sure that C is contained inside A cross B,
Yes, sir.
right? Because we are collecting sets from A cross BR, right? So if I prove that this is a sigma algebra and the set of all rectangles is contained inside C,
The
this
rectangle.
together would. Mhm. Yes, yes. Tell me.
We have to show that the all rectangles should belong to the collection
Right,
C.
right. So these two things you have to prove, right? That the
Yes,
rectangle should belong to C and that the sigma algebra, I mean, C is a sigma algebra. Then together, this would mean that C is equal to A cross B. And then our claim will be true that for every inside A cross B, SE alpha beta is inside A cross B. So, do you agree with the process?
yes, sir. So
Okay.
I was thinking that we should prove that that set S E alpha beta should be equal to the sigma algebra, and we have to show that the rectangle is inside that set. I
No,
was
no, but
going that.
SE alpha beta is not a collection of sets. SE alpha beta is a collection of points, right?
Yes, sir.
This is a collection
Okay.
of points.
Yes. Okay, sir.
So, see, the first question is that whether this collection C, whether it is non-empty or not, right? So, is this non-empty? So, what do you think? Is it non-empty?
C is non-empty.
Yeah. Why is it non-empty? Can you give me one element inside this?
I mean, if we took alpha and beta to be both 0.
Okay. No, but see, what I'm saying is you collect all those E such that SE alpha beta is inside A cross BR for every alpha beta, right? So the choice of alpha beta is not in our hand.
So the subset of C in itself is contained in C.
Which subset of C?
I mean, C itself, like C is a subset of itself, right, from set theory. So
No, no, no.
that's
Yeah, that is fine. I am saying, see, does this have any set? So can we find, let me just write a question. Question is, can we find some E inside A cross BR such that E is inside this collection C?
um. So if alpha is 0 and beta is 1, so xt belongs in
The
E.
space, I think the rectangle, the product of the whole space.
Right. Actually, Robin, could you continue? What were you saying?
So if we choose, so it's just a trivial example, right? If we choose alpha is, so we're given that x and alpha plus beta t belongs in E,
Mhm.
right?
Right,
and
right.
and x t is contained in the product of the set x cross R. So
Right.
I mean, if we show that alpha is, if we choose alpha to be 0 and beta to be t, right? That in
Oh,
its
no, no, no. But then, see,
beta to be
first of
1,
all,
so beta is equal
no,
to 1.
it should not depend on T, right? The choice. Plus, what I am saying is, see, whatever I have written here for all alpha beta, which means the choice of alpha beta is not with us, right? We have to check that SE alpha beta is inside this sigma algebra for every alpha beta. So we cannot fix alpha and beta something,
Okay.
right? So what Prasandeep said, we should follow that. See, the biggest possible set, let us try to see whether that set is inside the sigma algebra or not. So to see that, let us consider E as X cross R. Okay. So what is SE alpha beta? SE alpha beta is, look at all those X comma T in X cross R such that X comma alpha T plus beta, this is again inside X cross R, right? Because
Yeah.
this is our E now. But this is true for every X comma T. Is it not
Yeah.
the case? Right? So basically, I am saying that this is equal to X cross R, correct?
Yes.
And this is always inside A cross B, irrespective of what my values of alpha and beta are,
Yes,
Um,
sir.
right?
so instead of fixing it, I can just, like, I can choose any arbitrary alpha, beta, and R. So it's like I'm taking,
Exactly.
so
Exactly.
instead of, because I was I was looking at a very specific example. It's like if we fixed it, but yes, exactly.
Correct. Correct.
Entire
Okay.
space stay within the product.
Correct. So entire space is always within the product, and therefore X cross R is inside this collection C,
Yeah.
right? And therefore C is non-empty. Okay, at least C is non-empty, so one can think that C is sigma algebra. But then we also need to prove that the rectangles are contained inside C. So let us start with taking a rectangle. Consider a set of the form E cross F coming from A, this product BR. What does it mean? It means that E is inside A and F is a Borel set in R, right? Okay. Now let us consider this S E cross F alpha beta. This is the collection of all x comma t in x cross R such that x comma alpha t plus beta, this is inside E cross F. Yeah, this is the definition. But now let us try to see when an element can be inside this E cross F alpha beta. This is same as saying x comma alpha t plus beta is inside E. Sorry, inside E cross F. But this is same as saying x is inside E and alpha t plus beta is inside F, right?
Yes.
So I can also say that X is inside E and T is inside 1 over alpha times F minus beta. Yeah.
Yes, sir.
Okay. But then, okay, is this a Borel set?
Yes, it is.
Why is it a Borel set?
It's because it's an injective function. It's it's
Which
it,
function?
it's so for example, if we can define T as a function of elements within the Borel set. So it's injective.
No, no. Actually, see, there are two things here. One is inherently, I am assuming that alpha is non-zero, right? Otherwise, I cannot divide by alpha,
Yeah.
right? Plus, what I am using is that the Borel sigma algebra, this is translation and scaling invariant.
Yes, sir.
What do we mean by F minus beta? F minus beta means translate all the elements of F by beta towards the left,
Yeah.
right? And 1 over alpha means scale them by 1 over alpha.
Yeah. Yeah.
So since the Borel sigma algebra is translation and scaling invariant, the translation of F with beta is again in BR, and then scaling by 1 over alpha is again in BR. So
Yes.
overall,
Yes.
this set is in BR, provided alpha is non-zero. Okay, so let us do it for alpha non-zero. We will take
Yeah.
the case alpha zero later. Okay, so this is x comma t. I'm sorry, x comma t is inside E cross 1 over alpha times F minus beta. But then this is a rectangle, right? This is inside the set of all rectangles, which is contained inside A cross BR, right?
Aniruddha, can you explain why this is inside the rectangle?
Oh, because E is already in A, and we have just seen that 1 over alpha F minus beta is a Borel set,
Yes, exactly.
right?
Sorry.
So its
Yeah.
product is a rectangle.
Yes.
Okay.
Yes. Thank
So
you.
this is a rectangle. Rectangles are contained in A cross BR. So all in all, if alpha is non-zero, S of E cross F alpha beta, this I can write as E cross 1 over alpha F minus beta. This is inside A cross B. But what happens if alpha equal to 0? That is a condition we need to check separately, right? So
Yes.
if alpha is equal to 0, then S E cross F alpha beta, by definition, this is, look at all those x comma t in x cross R, such that x comma alpha t, but now alpha is 0, so it is 0 plus beta, x comma beta is inside E cross F. And here, okay, can you tell me what this set will be? What are the possibilities of this set?
Oh, can you be a little bit more specific? Like what kind of?
Okay, so I am saying this is, suppose we start with xt inside this S of E cross F 0 comma beta. Then I am saying that this is same as saying x comma beta is inside E cross F, right?
E cross F will be the same as X cross R, right?
No, no, E cross F will not be same as x cross R, right? This is same as saying x is in E
Oh yes,
and beta is in F,
it is an
right?
F. Yes, yes.
So the only two possibilities are that, so if I want to look at S E cross F 0 beta, the only two possibilities is E cross whole of R whenever beta is inside F and empty when beta is not inside F.
Okay.
Yeah. So do you agree?
Is that S of 0 and beta?
Yes, yes. S of 0 and beta, because we are assuming this alpha to be 0 now, right?
Yes.
So, see, the thing is, because what I'm saying, an element belongs to this set if and only if x is inside E and beta is inside F, right? So, x is inside E is there, so E cross something is going to be there. but that cross something, it is independent of T, right? This whole condition, it is independent of T. So whenever beta belongs to F, every x comma T, I mean, every T belongs to this set. So whole of R. But if beta is not in F, no such x comma T belong to this set, right?
Yes.
So there are only two possibilities. And even in this case, it is inside A cross BR. Because the first condition is a rectangle and empty set is inside the sigma algebra. So both these sets are inside A cross BR.
Ah.
Okay. So all in all, what we started with a rectangle E cross F. We proved that S of E cross F alpha beta is always inside A cross B. So let me perhaps I'll write it. So for a rectangle E cross F, S E alpha, sorry, E cross F alpha beta. This is inside A cross BR for every alpha beta. But then this means that E cross F must be inside C. This collection C which we have defined.
Yes, sir. The
Huh?
rectangle should inside the C.
So now the rectangles are inside C. Okay. And what is the next step? What do we have to do now?
So to show that it is a sigma algebra.
Correct. So we just have to show that C is a sigma algebra. Now, claim is that C is a sigma algebra. So how to do that? What are the things we need to prove to show that C is a sigma algebra?
We just have to show whether C satisfies the conditions for sigma algebra, which is the empty
Right,
set
correct.
itself.
Correct.
Are
So the first thing we need to prove is that empty set is inside C and X cross R is inside C, right?
yes.
But is this true?
The whole space it is a rectangle, obviously.
Right. And we have already started with that, right? To prove that C is non-empty, we actually prove that X cross R is inside C. So at least this part is true. What about the empty set?
I mean, if B does not belong to F, then it's the empty set, which also belongs in C again.
Exactly. So empty set itself, it can be written as E cross empty set. Whenever E is any set in A, and empty set is of course inside BR because
Yes.
it is a sigma algebra. Therefore, it is a rectangle, and rectangles we have proved that they are contained in C. Therefore, empty set is also contained in C.
Yes.
This is also there. Now, what is the next thing we need to prove?
The complement
The
Correct. We
belong
need
to.
to prove that C is closed under complements. So whenever E is inside C, this means E complement is inside C. So, but see, E complement is inside C. This is same as saying S E complement alpha beta. This is inside A cross BR for every alpha beta. Right? Let us
Yes.
calculate this S E complement alpha beta. By definition, this is collection of all x comma t in x cross R such that x comma alpha t plus beta. This is inside E complement. Or what is the same? I can write it as x comma t in x cross R such that x comma alpha t plus beta. This is not in E, right?
Yes.
Yes.
Yeah. But what is this set equal to then?
No. This is the empty set.
No,
Both
it is not
elements
the empty set.
belong to.
Prasandeep, could you repeat?
So the two either x not belongs to the E or alpha t plus beta should not belongs to the.
No, no, no. E may not be a product. E may not be a product of two sets. See, okay, let me write it
Yes.
this way, then it will
Yep.
be clear. See, xt is inside SE alpha beta if and only if x comma alpha t plus beta is inside E, right?
Yes.
Okay. But then xt is not inside SE alpha beta if and only if x comma alpha t plus beta is not inside E.
Yes.
Yeah. Prasandeep?
Yes, sir.
But the left hand side means that xt is inside SE alpha beta complement.
Yes, sir.
Correct? While the right hand side, it means that xt is inside S of E complement alpha beta. Correct?
Yes.
Yes,
So
sir.
therefore, what do we conclude? We conclude that SE complement alpha beta, this is equal to SE alpha beta
Complement.
whole complement. Right? But by assumption, since E is inside C, SE alpha beta is inside A cross B, but this is a sigma algebra. This implies SE alpha beta whole complement. This is inside A cross B, but that is nothing but S of E complement alpha beta. Yeah, just
Yes.
this,
Oh,
right? And this further implies that E complement is inside C,
Ah.
right? So this way we prove that C is closed under complements. Now, what is the third property we need to prove?
The unions are also in A cross B.
The countable unions are inside A cross B, right?
Yes.
Inside C. So if we have a sequence En in C, then if I write their union as capital E, this is again inside C. So see, the idea is this, right? Ultimately, we need to calculate SE of alpha beta. So let us write it SE alpha beta. This is by definition all those xt in x cross are such that x comma alpha t plus beta, this is inside E. But E is our union. So
yes.
x cross R such that x comma alpha t plus beta, this is inside the union of all Ens. Okay. So let us again, let us try to write it in terms of some equivalent statements. So a point x comma t belongs to SE alpha beta if and only if x comma alpha t plus beta is inside the union. Okay, but what does this mean?
It should be in at least one of the.
Exactly. So there is some n,
For which X and alpha T plus beta belongs in E.
right? This is inside En. But what does this mean?
It belongs to at least one of the SE of alpha beta.
Correct. So there is this n such that x comma alpha t plus, oh, sorry. I mean, not alpha t plus beta. X comma t belongs to S En alpha beta. Yeah.
Yes, sir.
Yes.
But then, this means that xt is inside this bigger union S of En alpha beta. So all in all, what we prove is Se of alpha beta. This is equal to union of Sen's alpha beta. And by assumption, all of these are inside A cross B. So this whole union is inside A cross B, right?
And therefore C is a sigma algebra. Because uh,
Precisely.
C is basically the collection of the of all the SEs such that
Yes, yes, precisely, precisely. So therefore, C is a sigma algebra, and we are done, right? Therefore, C is whole of A cross B, and that is what we wanted to prove. Because now what we have proved is, you take any element in A cross B, this SE alpha beta is again inside A cross B.
Yes.
So, any
Just
questions here?
misunderstood the technique. I would rather say.
Uh-huh.
Yes, I was thinking that how rectangle should belong to the other set given, not getting it rightly. Okay, sir. Thank you.
Okay, so see, for rectangles we have to calculate, right? So here we have done it. Let us start with a rectangle, and then what do we mean by S of E cross F alpha beta? Write the definition. So a point is inside S E cross F alpha beta if and only if this x comma t is inside E cross some other set. That set is again a Borel set. So this, the corresponding to the rectangle E cross F, the set S E cross F is again a rectangle, and
Yes,
the rectangles are
yes,
already contained in A cross BR.
Aniruddha, if you can show the same technique for the second question, I think that would make it a lot clearer.
Yes.
But, because I think I have the same question as well, which is
Okay.
how
Okay.
to show that the rectangles are in C as well.
Yes. 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 So again, here, what will be the C? Can you tell me?
C will be the set of all E's
Mm-hmm.
contained in A cross in A cross the Borel the Borel
Yeah.
sigma algebra, such that, so if we decided that SE is going to be um, all the uh, all the
Okay. Let
pair
us write it. Yeah.
all the pairs of xt such that xt belongs in X cross R, such
Mm-hmm.
that X and the polynomial function ft, they belong in E.
Exactly. But then this depends on F as well, right?
Yes.
So let us write it S E F. So the collection C is that all those sets of A cross B are such that SEF is inside.
yes,
Yeah,
Uh,
where is it?
it's in A cross B.
It is in A cross B. For
The
which
Borel.
F? For every F, right?
Yes, for every F.
For every polynomial F. So
Yes.
usually polynomials are denoted by this Px. This is the space of all polynomials. In one variable with real coefficients. Right. So we want to prove that C is a sigma algebra. Again, the first question should be whether this collection is non-empty. So what do you think? Is this collection non-empty?
Yes, it's obviously non-empty. It follows
Why?
from the previous. So uh, just like the previous one, if we showed that if we took E is equal to X cross R,
Right.
so the constant are always polynomial.
Yes, constants are polynomials. So
So the the whole space rectangle should always belong to the.
no, no, but we have to prove it for all polynomials, right? We cannot fix a polynomial and prove it.
It is obvious. Yes, it can be any polynomial.
It could be any polynomial. So E is equal to X cross R. In that case, SEF, that is again all the points xt in X cross R, such that x comma ft is inside X cross R. But that is just true for all x and t. So this is again X cross R,
yes.
which is inside A cross BR, and therefore C is non-empty. Okay. Now the next thing is we have to prove that C is a rectangle. Rectangles are inside C. So let us
Yes.
start with a rectangle. Consider E cross F in the set of all rectangles of A cross BR. And let us construct this S E cross F. F. So can you tell me what this collection is?
Uh,
So A cross F
Mm-hmm.
belongs to the product sigma algebra such that
No, no. We have to see this S of E cross F, right? Look at this and then tell me what is S E cross F. Just call this some different set. No, let us call it as a G.
this means I don't know. This means that X belongs in E
Right.
and
So
FT
yeah,
belongs in F.
collect collect all those xt in X cross R such that X is in E and Ft is in F,
Yes.
right? But
Yeah.
Ft is in F. This I can say X cross R such that X is in E and T is in the pre-image of F, right?
Yes.
yes, sir.
So this I can write E cross the pre-image of F. Now the question is whether this is a Borel set.
It is right. The pre-image of a Borel of a Borel sigma algebra is again in the Borel sigma algebra.
Yeah, that is because polynomials are continuous.
Yes.
Since F is a polynomial, F is continuous, which implies F is Borel measurable, which implies F inverse of F is
Is
inside
it?
the Borel sequence.
Yes.
Right. So
Yes,
this is
sir.
again a rectangle then. Yeah.
Yeah.
So therefore S of E cross FF, this is inside A cross BR for every F. Because here we never used any property of the polynomial, right? Any for any polynomial, this is true. And hence E cross F, this is inside C.
Yes, sir.
Aniruddha, just a quick question. So over here we use the fact that the pre-image of a Borel set or Borel set, subset is again uh, in the Borel sigma algebra. Why couldn't we? And I think that's what I was getting to in the first question as well. Is that what if we chose the pre-image of all the T's to be a Borel set? And by definition, I know that you use the translation and the invariance properties for the
Right,
first
right.
question, but why couldn't we use this property, which is the fact that if we chose so alpha plus beta t is a
Uh-huh.
full f t.
Okay, okay. Directly you wanted to use it, but
Yeah, that's exactly what I was getting to.
acha, acha, I was thinking something else. Yeah, that is also fine.
I can use that. I can use
Yeah,
that over there as
I
well, right?
misunderstood. I misunderstood you.
That's what I was getting to. It's like because I remember that property very well, so it's pretty easy because I'm doing real analysis as well. So I was like,
Okay.
let me use this property. So I can use the continuity property in question one as well, right?
Yes, yes, yes. In fact, the translation invariance it comes from continuity.
Yes, yes.
Otherwise, how would you prove that the Borel sigma algebra is translation and scaling invariant?
Okay, thank
That
you
is
so much.
from continuity.
Practice.
That time I completely misunderstood you. So anyway, you can use that.
It's okay. I think I was a little unclear in how I wanted to go about it
Okay.
because I was saying that it's injective, and I'm
Huh.
sorry. Thank you so
Huh.
much.
Okay, okay. So now you can proceed from here, right? The next part is you have to prove that C is a sigma algebra. Yes, Prasandeep, can you proceed from here?
Yes, sir. Obviously, sir, the whole space we have already showed that it is inside that set. So obviously, the whole space
Yes.
is
Right,
inside
right.
that.
No, no, I don't want the proof. I'm asking you whether you can write the proof yourself or not.
Obviously, we will do it.
You can do it, no? Okay.
Yes, sir, we will do it.
What
We'll,
about
we'll, we'll try and attempt. I'm not sure whether if you showed us I mean look, exams are 3 weeks away. If you showed us that
yeah,
that
yeah, yeah. See, okay, okay. Let us go through it quickly. See, the first point is we need to prove empty set is inside C, X cross
we've
R is
already
inside C,
yeah.
right? But this second part we have already shown. The first part follows because this is inside the set of all rectangles, right?
Yes, sir.
Why does the first one follow? Um,
Yeah, because empty set is a rectangle, right? Empty set I can write as E cross empty set,
oh
where
yes. Sorry,
E is
sorry.
inside the first sigma algebra and empty set is inside the second sigma algebra. So it is a rectangle. So the empty set inside C and X cross R inside C follow easily. The second part is what we have to prove that C is closed under complements. So whenever E is inside C, we need to prove E complement is inside C. So let us look at SE complement F. This is the collection of all XTs such that X comma FT is inside E complement, but that means it is not inside E. Right? But then this is equal to SEF whole complement, isn't it?
Yes,
Yes, sir.
And this is inside A cross B for every A.
and now we invoke the sigma algebra property of SEF
Correct.
as well.
So here we are invoking the sigma algebra property. And therefore, E complement is inside C. And the third thing we need to prove is that uh, the unions are inside C whenever ENs are inside C.
It's the same as the first one. I don't think we need to. Yeah,
Exactly, exactly. So
it's the
if
same
you
as
notice in the first one, to prove it that it is a sigma algebra, we never use the property that this function was just alpha t plus beta, right? Here I
yeah.
could replace any continuous function. It would just proceed the same way.
So it as long as the function is continuous,
Yes.
we can
In
we can
fact, in fact, as long as the function is Borel measurable, I could proceed the same way, right? Because the only property of the function which I have used is here to prove that the rectangles are inside, right? This is the
yes.
only property where I have used it. So any Borel measurable function would work.
Aniruddha, this is a very dumb question, but
Mhm.
um, with countable union, that means that n goes from one to infinity, right? Not n goes to one to like some finite number.
Yes, it just keeps on going,
Yeah,
never
because
stops.
I got a little confused with countable additivity and countable union. It's just because I get confused with notations. So I'm sorry about that. I
Oh,
just wanted to
okay,
clear
okay.
that.
Yeah, countable union means the union keeps on going. We don't stop at any finite thing.
Okay. So Aniruddha, just to clarify, when
Uh-huh.
using the same algebraic technique for product spaces, we're actually doing it in 3 steps. So the first step is we're showing that C is non-empty.
Yes,
The second is to show that all the rectangles are contained in C.
yes,
And then finally we show that C is a sigma algebra.
correct, correct.
So these are the 3 steps. These are
Yes,
the three
these are the three steps. I mean, this is the usual way one proceeds. I mean, they are not necessarily in the same order. You can prove that C is a sigma algebra first, and because see, once you prove it is a sigma algebra, it is automatically non-empty, right? Because empty set is inside, and the
yeah.
whole space is also inside. So proving it is a sigma algebra also proves the first step.
Yeah,
And then you prove that the rectangles are inside it. Even that
that
will give you the result.
okay. Uh, can this example? So these two questions
Mhm.
we can apply it to question 3 as well, right? Because question 3 is basically, I think it's the same thing, which is
No, actually, question 3 is a direct answer question. See, we have already seen that the sigma algebra generated by C cross D, this is contained in the sigma algebra of C cross sigma algebra of D, right?
yes.
Yeah, so can I say that the Borel sigma algebra of R2 is definitely contained inside the Borel sigma algebra of R cross Borel sigma algebra of R?
Yes, by invoking the previous line.
Yeah, so just by this purple line, I can see this, right? We just need to prove that they are equal. But there also we have a result. The result says that if, sorry, I mean, if there exist CNs inside C, so this is all the script C's, and DNs inside D, such that union of Cn is X, union of Dn is Y, n from 1 to infinity, n from 1 to infinity, and Cns are increasing, Dns are also increasing, then the sigma algebra generated by C cross D is equal to the sigma algebra of C cross sigma algebra of D. I think this must have been done in one of the lectures, right?
This is actually in one of the questions as well.
This is one of the questions.
Yeah, question 5, 4, and 5. Something
Oh,
similar. I mean, it's not directly in the question, but it's something similar. The
question
unique,
4 and 5.
yeah.
But question 4 and 5 is something else.
It's sections. I know,
Yeah,
but
yeah,
yes,
it is about sections.
it's about
But
sections.
see, this result, the result which I have written must be done in one of the lectures.
Yes, sir. It has
Huh?
proved that.
It is proved in one of the lectures, right? See, if it is
Yes.
It
not proved, you can find it in the book. I think chapter 7, somewhere it is there.
I'm pretty sure the professor proved this as well, because this kind of follows. I think this followed from or after the sections where he explains
Yeah,
section.
yeah, yeah. Yes, yes, yes. After the sections, yes.
Yes, yeah, this was proved.
So the thing is, just a minute. Yeah. Can you hear me? Hello.
Apart near the
Yeah, yeah. You can hear me, right?
yes, yes.
Actually, my earphones got discharged, so I removed them. Anyway, so see here what we have to do. We have to just produce a sequence inside R, which is increasing, and its union is whole of R. Can you produce such a sequence?
Any monotonically increasing bounded sequence in R will satisfy,
Right.
right?
So basically, if I just choose my Cn to be minus n comma n, then this is an increasing sequence, and union of Cn's is whole of R. Right.
Yes.
Just these two conditions are satisfied. Therefore, B of R2 is equal to BR cross DR.
yes, sir.
So it is, but I mean, it is a direct question. We don't have to compute anything here.
I was just trying to understand the proof, but thank you so much, because I knew what the answer was. I knew what the answer was. I was like, it made sense. But I just wanted to find a proof. Okay. Thank you so much for that.
Okay, okay.
The other questions were pretty easy, but it's just the first three that kind of
Yeah, I think other questions also they were done in the lectures, right?
yes, exactly. And they were just very simple proofs. It's just to show the fact
They are
that you
basically set theory. Nothing
yeah.
about measure theory there, right?
Yeah, exactly. It's just the first three questions, especially the first two that I really could not. I was like,
Yeah,
I
yeah.
went,
The first question actually was the tricky one because if you get the idea of the first question, you can solve the second question as well. Right?
Yes. Thank you so
Okay.
much for that. I know that you're going to be uploading these, right?
Yes, yes, I'm going to upload it. So, okay, any other questions?
Uh, I had a question from week 9. I still don't understand Lebesgue the Lebesgue integral.
You don't understand what?
The Lebesgue integral. Like, I understand how we can equate the Riemann integral to the Lebesgue integral, but it's just uh, this one, and there's this other one which is from week 10. The x goes to mu of y.
Huh. Right,
Yes,
right.
that function. I can't understand that. If you can, I can catch up on the Lebesgue integral part, but if you can explain these two.
These functions, right?
Yes, yes,
So see, what does it mean? Let us try to see. E is given a subset of x cross y. From this set, we can construct Ex, which is a subset of y, which is a subset of y,
yes,
and Ey, which is a subset of x.
yes,
Okay, but this is for a fixed x, right? If I change my x, then Ex is going to change.
yes, because the y's depend on the x. The y's
Right,
depend
right.
on. Yes,
See, it is the better way to understand is, let us just draw some set E. Suppose this is my E, then Ex means fix an x. Look at this line. Then this is my, I will project it here. Then this part, this is my Ey. Sorry, this is my Ex. On the
yes,
other hand, let us look at this horizontal line. Look at this intersection. Project it here. This part is my Ey,
yes,
right? So if I change my x, Ex is going to change. If I change my y, Ey is going to change very naturally.
yes.
So this is also for a fixed y. So let us define a function, say phi, from x to r. How will I define it? At any point x, let us measure Ex.
Okay.
Right? This is going to be a function, right?
Yes,
Okay. And similarly, let us define C from y to r as C of y as the measure of Ey.
yes,
This is also a function, right? So basically, this notation is for the function phi, and this notation is for the function c. And what we are claiming is that both of these functions are measurable.
yes. So when I was trying to when I was trying to go through the measurable part, that's where I got confused. Is so how do we show that phi and phi and phi they're measurable? Um, give,
Right. So do you have the proof with you right now? Because I do not exactly remember the proof of measurability. Right. We just have to prove that the pre-images of Borel sets are Borel, right? Something like that.
yes,
So the mu and b should be the finite measure for this function to be
Yeah, I could
defined.
not understand.
So the measures should be the finite measures.
No, no, I'll just make it in the extended real numbers then.
Okay,
Okay, so these functions are all extended functions.
okay, okay.
Right, right, right. So, just a minute.
I think he used the professor used the monotone class property.
Right, right. So we have to look at all those sets where they are measurable. These functions are measurable, right?
Yes,
So basically, what we are going to do? Let us again look at this collection E from E contained in x cross y, such that phi Yeah, again, this phi depends on E. So let me write it phi E and CE. Phi E and CE are measurable. Again, the same questions that what happens, is C non-empty, is rectangles contained in C, is C a sigma algebra and all, right?
Aniruddha, just a quick question. With
Uh-huh.
because EX is actually a subset of Y, right? Why are
Correct.
we why are we measuring it as a function of X?
Because once you measure, see, this is a number, right? This thing is a number,
Yeah.
okay? But it depends on X.
Oh, okay. So it depends on X because the choice of X determines
Correct. It
the
determines
Y.
EX, and then EX determines that number, right?
Oh,
Yeah.
okay. And same for EY.
Same for EY also.
The choice of Y determines the values of X.
Exactly, exactly. I mean, choice of Y determines the values of CEY. I mean, this measure, this number is dependent on Y.
Which is dependent on X, the values of X, which is why EY is actually a subset of the set X.
Right, right. Yes. So does
Okay.
that answer your question?
Yes, now I understand. And now I think I understand the monotone class property as well, because it's a lot easier to prove it using the monotone class.
Right, right. So first you have to prove that the algebra is contained here, and then this is a monotone class. So overall,
With
the sigma algebra.
the another just a quick question with the monotone class, right? All we
Hmm.
have to show is we have to take an increasing sequence and show that um, the intersection of the sequences, they converge to one point.
No, no. Why 1 point? That is the finite intersection property that we don't want. Monotone class means if you take a increasing sequence, then that union is inside C. If you take
Yes,
a decreasing sequence, then the intersection is inside C.
yes. Sorry. So closure under both union and intersection. Yes,
Increasing unions and decreasing intersections.
yes, yes. So it doesn't. So it doesn't necessarily have to be an increasing sequence, does it?
Yeah, it has to be increasing sequence. See, for monotone class, there are only two properties we require. First is En contained in En plus 1 implies union of En is inside this, well, let us call it as M. Yeah, maybe M. Okay. M. And the second one we require is whenever En contains En plus 1, this implies intersection of En is inside this M.
So, so it's both increasing and so increasing sequence union has to be union is an M, and for
Correct.
decreasing sequence the intersection will be in M.
Right, right, exactly.
Okay.
So now you can prove this, right? That this is a sigma algebra.
Yes. So do it for both EX and EY,
Right. Yes.
and we're pretty much done with the proof.
Yes, but we have to prove that it is also an algebra. If you are going to use the monotone class, then we require two things. First is it is an algebra, and second is it is a monotone class, right?
But if we show that it's a sigma algebra, doesn't that already satisfy the fact that it's sigma algebra?
But I think in the proof in the lecture, he has shown that it is an algebra first, and then it is a monotone class, and
Uh,
therefore it is a sigma algebra.
exactly, Aniruddha. That's where my question was, which is, can we directly show this is a sigma algebra? Because if we show that it's a sigma algebra, we automatically satisfy the condition that it's an algebra.
I will have to check. I don't know at this moment. I will have to check if there is a direct method.
Because if we show that it's a monotone class, right, which we can show from here, and if we show that it's a sigma algebra,
no, but sigma algebras are automatically monotone classes.
Yes, exactly. So I mean,
no. We have to prove that it is an algebra plus a monotone class.
And hence it's a sigma algebra.
Correct. If I say it is a sigma algebra, it is same as saying it is an algebra.
Yes.
Plus monotone class.
Yes.
Right. So I think in the lectures we are following this thing.
I think it's easier to show that it's an algebra, if I'm not wrong. Then
yes, it is easier to show it is an algebra. That is true. Algebra only requires that finite unions.
Yes. So we have to show that C is a sigma. C is an algebra, and we have to show that all the ENs that are contained in C are monotone classes.
Correct.
And hence C is a sigma algebra.
Right. That is the process we have used in the lectures. Although I don't know if we can directly prove C is a sigma algebra or not. I will check and I'll let you know.
That would be great.
Yeah.
I don't think there is, but if there is, I mean, why not?
Yes. If there is a direct method, it would be better.
Thank you so much. I think that's what I was mostly confused with the notation, which is how do we phi x is basically, it depends on x because the y's that we're choosing depend on x, and
Correct.
similarly phi y is dependent on y because the x's that we're choosing, they depend on y.
Right.
Okay, that's
okay.
It takes a bit to settle down, but now I understand. Thank you so much.
Okay, fine. So,
thank you so much.
Yes, sure. Prasandeep, do you have any questions?
No, sir. Till now, not any other question.
Okay. So perhaps let us stop. I wanted to do a
Okay,
few examples on this Fubini theorem, but that we can do next time.
okay, sir. Thank you.
So